Hi everyone, my name is Wenbo Jiao. Today I will teach you about transfer learning using deep networks. This is one of the most useful techniques in modern computer vision. So let us get started. So what is transfer learning? The idea is simple. Instead of training a network from scratch, we take a network that was already trained on a large data set and reuse it for different tasks. Let me give you an analogy. Imagine someone who already knows how to play piano. If they want to learn guitar, they don't start from zero. They already understand the rhythm, rhythm and music theory and hand coordination, so they can learn guitar much faster than someone with no musical background. Transfer learning works the same way. A CNN trained on ImageNet, which has 1.2 million images across 1,000 categories, has already learned to detect the edges, textures, shapes, and object parts. We can reuse those learned features for new tasks, even if we only have a very small data size. Look at the comparison at the bottom of the slide. Without transfer learning, if you train from scratch on a small data set, you get overfitting and poor features. It can take weeks. With transfer learning, you reuse ImageNet features and only train the classifier. You get better accuracy with fewer images in minutes instead of days. Now, why does transfer learning actually work? The answer is the feature hierarchy. When a CNN is trained on a large data set, different layers learn different things. The early layer learn very general features, things like edges, corners, simple textures, and color gradients. These features are useful for any image task. It doesn't matter if you are classifying dogs or X-rays or clothing. The middle layers learn more complex patterns, things like curves, repeated textures, and combinations of edges. These are still fairly general and transferable to similar domains. The later layers learn high-level features, things like object parts, faces, wheels. These are more specific to the original task, so they may need some fine-tuning. The final layers, the classifier layers, are completely task specific. They output this is a cat or this is a car. This must be replaced for any new task. The key insight is at the bottom of the slide. Early and middle layer features like edges and textures are universal across vision tasks. Only the final classifier layers need to change. That is why transfer learning works. Now, let me walk you through the process. These are three steps. Step one, load a pre-trained model. You start with a model that was already trained on a large data set, usually ImageNet. Common choice include ResNet, which is lightweight and fast, VGG16, which is simple and popular, and Google the net, which is efficient. The convolutional layers in these models have already learned general visual features from over 1 million images. Step two, freeze and replace. You freeze all the convolutional layers. This means you set requires grid to false, so their weight will not be updated during training. Then you remove the original classifier, for example, the 1000 class ImageNet output layer, and replace it with a new classifier for your task. For example, a 3-class output, only the new layers will be trained. This means about 95% fewer trainable parameters. Step three, train and optionally fine tune. You train the new classifier on your small target dataset. This usually converges very fast, in minutes, not hours. Optionally, after the classifier is trained, you can unfreeze some or all of the convolutional layers and fine-tune the whole network with a very small learning rate. Be careful, fine-tuning can overfit quickly on small dataset. Always watch your validation set. Let me show you a real example from this course. In Project 5, Task 5, we use transfer learning to classify Greek letters. The source task was amnest digit recognition. We trained a CNN on 60,000 digit images, and it reached 98.3% accuracy. The network learned to detect edges, curves, and stroke patterns. Now, here is the interesting part. For the targeted task, we want to classify Greek letters, alpha, beta, and gamma, but we only had 27 training images. That is just 9 images per class, way too few to train a network from scratch. So what did we do? We froze all the convolutional layers and the first fully connected layer, that is 21 690 parameters frozen. Then we replaced the last layer with a new three-class output. Only 153 parameters were trainable. The result is the network reached 100% accuracy in just eight epochs of training. Why does this work with only 27 images? Because the frozen convolutional layers already know how to detect strokes, curves, and line junctions from digital training. Greek letters are made of the same visual building blocks as digit, just combined differently. The new last layer only needs to learn this combination of strokes means alpha. That combination means beta with 153 trainable parameters and 27 images. That is about 6 images per parameter, which is plenty. Now, when should you use transfer learning? It depends on two factors. How similar is your target domain to the source domain, and how much data do you have? Let me go through the 4 cases. Bottom left, similar domain and small data size. This is the best case for transfer learning. Freeze everything and train only the classifier. For example, using ImageNet features for medical X-ray classification with only 200 images. The pre-trained features transfer well and freezing prevents overfitting. Top left, similar domain and large data size fine-tune the entire network with a small learning rate. For example, ImageNet to bird species classification with 5,000 images, you have enough data to safely adjust all layers. Top right, different domain and large data size, you might need to fine-tune only the later layers or even train from scratch. For example, ImageNet to satellite image classification, nature of photos and aerial views looks very different, but having lots of data helps you learn new features. Bottom right, different domain and small data size. This is the hardest case. Transfer only the early layers and be very careful with fine-tuning. For example, ImageNet to microscope cell classification with 50 images. The early edge detectors still help, but the later features may actually hurt. If possible, collect more data. Here are some practical tips, things to do and things to avoid. On the do side, always match your pre-processing to the source model. If you use an ImageNet model, you need to use ImageNet's normalization values. Using wrong normalization is a very common mistake. Use a small learning rate for fine-tuning, about 10 to 100 times smaller than training from scratch. Monitor your validation set closely. Stop fine-tuning when the validation lose starting going up, and always try the frozen approach first before fine-tuning. On the don't side, don't use a large learning rate when fine-tuning. This will destroy the pre-trained features. Don't fine-tune the entire network on a tiny data set. You will overfit instantly. Let me summarize the 5 key takeaways. First, transfer learning reuse features from a large data set to solve a new task with limited data. Second, it works because early CNN layers learn universal features that are useful for almost any vision task. Third, the process is simple. Load a pre-trained model, freeze the convolutional layers, replace the classifier, train, and optionally fine-tune. Fourth, how much to freeze depends on domain similarity and data set size. And fifth, transfer learning is the single most important practical technique in modern computer vision. Most real-world applications use it because collecting millions of labeled images is simply not practical. Thank you for listening. That is the end of my presentation. Have a nice day.